The Best Way to Explain It, Episode 11. Greetings, everybody. Welcome back. Another episode of The Best Way to Explain It. I'm Scott Olson. That's Breckan Nielsen. Here with the podcast that has somehow lasted longer than Pokemon Go.
Dude. No, we haven't. When
did you quit playing? Or you never started, did you?
Still playing. No, just kidding. I never started. I wasn't big on it, you know? I'd rather play like the actual game than walk around and pretend to play it.
That's fair. And there was a lot of stuff that was just kind of annoying with it.
Yeah.
Like battling was dumb, and I don't know. I played it for 2 weeks.
Yeah. I have friends who still have it and they still use it as like their way to get exercise. I just didn't want that many Rattatas on my phone.
Yep. No, it's that's definitely an issue.
Can't have too many Rattatas.
Right. Oh, basically what I wanted, though, with the game was I wanted it to be Pokemon, except instead of, like, us, walking around on our phones, like, we physically walked around in the world.
Yeah.
Like, yeah. I don't know why that wasn't the I don't know what you call it, the design of the game.
I got you.
I don't know.
Well, so what do you mean, like, walked around in the world?
So, like, okay, we do all the same things, like all the mechanics are the same as like in the Game Boy games.
Okay.
Except instead of like, just using the D-pad to walk around,
yeah,
like we could just physically walk around in the world.
Okay.
And that was how we got around to places.
Okay, so like would they physically map like the place that you live, or would they just have the like Pokemon world and then measure your steps?
Well, they did map the place where you live in the game now, or in the game that they released.
Yeah.
So I don't know why that wasn't just so you could have like local gyms, but like gyms would be like actual Pokemon gyms.
Yeah.
I don't know. And you could battle people. I don't know. They might have added that in though.
Okay.
After I quit playing.
Yeah.
Anyways, Pokemon Go.
we could do an entire episode just talking about how Pokemon Go failed.
Oh gosh, yeah, that would be a long episode. Okay,
yeah.
But there's something I wanted to talk about, and This is kind of cool. We're gonna be we're gonna be doing a giveaway. So yeah, ears perked up right now. Giveaway, right? So so what we're giving away, we're gonna be giving away can I say giveaway more times? I don't know.
I double dog dare you to say giveaway 10 times.
No.
Oh.
Okay. So we're going to be giving away an Amazon Echo. So yeah, that's pretty cool. And the way that you enter this giveaway is you have to leave us an iTunes review. And it doesn't have to be good. I mean, we'd prefer good reviews, but seriously, just leave an honest review. Leave something. Say like if you like the show, leave something that you like about it. So like don't just say great show, 5 stars, I mean, okay, you could say that, but we would encourage you to say something specific if you like it, and also just be honest with it. And the way that you enter, so you leave that review, and then you're going to take a screenshot of that review, and you need to email it to me at scott@thebestwaytoexplainit.com, and that will enter you into the drawing. Now, like we said, it doesn't have to be a 5-star review. Like you're going to be entered one time, whether or not you give us 5 stars or 1 star. Like we said, we prefer 5 stars, but be honest.
we just like you better if you give us 5 stars.
Right. We won't begrudgingly send you the Amazon Echo.
Yeah. There won't be any passive aggressive post-it notes on the inside if you make us,
If you give us a 5-star, the only thing we'll send you is an Amazon Echo. Whereas if you give us 1 star, there might be other things in there.
Ooh. Mystery.
Like, not good things.
Oh.
No, but seriously. So yeah, we'd just appreciate if you did that. And be sure to send us a screenshot. And do it quickly so that way, because we're just going to accept the first person that send. The reason we're going to have you send a screenshot is so that way we don't get multiple entries. People just screenshotting other people's to send to us. And that way it's easier to correlate who is who. And so that way, yeah, we'll just get in touch with you to get your address to send you the Echo once we do the giveaway. And this is going to run, I think, for about a month. Okay, so December 14th will be the last day you can do that. Because today, actually, you know what? Today, we're recording this on November 14th. When's this one coming out?
17th.
17th. Okay, December 17th we'll end the giveaway. So you have a month to leave a review, and we'll remind you a few times. And so, yeah, that would be cool. And anything else you want to say about that?
I got nothing.
All right,
just leave us a review, or else.
Yeah. Or else you won't get the Echo.
Yeah.
Yeah. Maybe you guys don't want the Echo. Maybe if nobody leaves a review, I'm keeping it.
So that the NSA can spy on you instead of our listeners?
Basically.
Okay.
Yeah.
Cool.
All right. But, Breckan, how would they spy on us? Would they do it on the internet?
Weird. I don't know.
Okay. It's odd when I transition to myself.
Yeah. I don't know. I don't know how they spy on us. I thought they had like a person that followed each individual person. So really there's like a person following you and a person following me, and they just they're about 5 minutes behind each of us,
Gotcha. So half of the world works for the NSA.
Yeah.
Cool.
Yep.
All right. Well, like I was just talking about though, we're continuing on in our internet series. This is the fourth part in a 6-part series on the internet. And so we're going to get started explaining the network layer of the internet. So let's begin. So if you remember last time, this is a series, like I said, so I'm assuming that you've listened to the other parts on the show, which you can look at easily at thebestwaytoexplainit.com/internet. And if you remember back to last time, we talked about the link layer of the internet, which was the layer at which access to the physical layer is controlled. Because since all the physical connections need to have some controls on them and how they work, we have the link layer, right? So now we're going to get into like the really complicated and interesting stuff, or at least I think it's the interesting stuff. It's the network layer. So the network layer is where you get into things like routing and connecting different networks rather than just different devices. And most of what we're going to talk about is probably going to include different acronyms and stuff like that you might have seen if you've ever used a computer for any significant amount of time. So why do we need the network layer? I'd like to start with that kind of question. Well, if you remember back from the last episode, we talked about the distinction between LANs and WANs. And if you don't remember that listen to that episode, thebestwaytoexplainit.com/9, and that'll take care of you. So the LAN was our local network, which was like your own personal Wi-Fi that you use at home. And then the WAN was the wide area network, which I said was the whole internet. Now, it doesn't have to be the whole internet, but that's an example of a WAN. So that's how I use that.
Cool.
Now, within the LAN, we can use really specific technologies that format the data in a specific way in order to send data in the most efficient way possible, right? But these formats and technologies they're not uniform across the whole internet. Like different companies, homes, schools, they all have different needs, so their LANs are going to be differently configured. But we still want these places to be able to communicate with each other, right? So the network layer is going to provide what's called routing, which takes data from within a device in the LAN and then routes it to other devices through the WAN. Does that kind of make sense?
Yeah.
Okay, cool. So that's kind of the whole point of the network layer.
Wow.
Now, if
that was a quick one.
Yeah, okay, that's it. Oh, no. So if you remember that when talking about the 5 layers of the internet, we need to know what addresses are used at that layer and then what the protocol data unit is, or the PDU. And if you remember, we didn't really have an address at the physical layer, but the PDU was a bit. And then for the link layer, we had the MAC address, or the physical address, and then the frame was our PDU. And in the network layer, we have the IP address as our address, and our PDU is the packet. Okay, so undoubtedly you've heard of IP addresses before if you've ever used the internet, but there's probably a good chance you don't know what their purpose is. Now, IP stands for Internet Protocol, which is sometimes what this layer of the internet is called. But what's in an IP address, though? Well, if you've ever seen one, it probably looked something like 192.168.1.50 or something like that. It's going to have that sort of format, the dotted decimal format. So an IP address with 4 sets of numbers with dots separating them is an address that is in the so-called IPv4 configuration. Now, IPv4 is just what it sounds like. It's Internet Protocol version 4. Now, there's also going to be Internet Protocol version 6 or IPv6. I don't know what happened to IPv5, but I guess IPv6 is just so good it skips over IPv5.
Even numbers are better.
Right, yeah. I seriously don't. I should have looked that up. It's just kind of odd. But we're going to talk about IPv4 first, since I think you kind of need to understand it to understand why IPv6 was created. So IPv4 here. So an IP address is used to identify devices that are connected to the network layer. So in a similar way that MAC addresses identified the physical device in the link layer, the IP address identifies the device in the network layer. Now, unlike the MAC address, the IP address of a device can change. I mean, I know MAC addresses technically can change too, but they don't. Well, we talked about the spoofing and whatnot in the last episode. But IP addresses can change and likely will change every time the device is going to connect to the network because it's going to get assigned an IP address. So when a computer connects to a network, it's going to get this IP address in dotted decimal format. But this dotted decimal number is more than just like a random number that it's assigned. There's actually quite a bit of information for the network within this number. It's stored within this number if you just know how to read it. Now, if you remember back to what I said about routing, the router, which is what we're going to talk about that a little bit later in this episode, it uses the IP address to figure out whether or not the information it is receiving from the device ought to stay on the LAN or if it needs to go out to the WAN. But, can it just tell which device to send the information to based on the destination IP address? Well, no, it can't. And this is the problem with IPv4. So, does that all make sense? Like what the IP address is supposed to be for?
Yeah. If you want to know what happened with the IPv5, though, I got a little something on that.
Yeah, dude, go for it.
It looks like the IPv4 was released with the original kind of start of the internet that you can listen to on the first part of this internet series, and then IPv5 would be the next generation, but they already used that to identify the protocol, the Internet Stream Protocol, I think.
Okay, I haven't heard of that.
Yeah, I'm just I'm looking through this really quick.
That's fine.
And it gave these stream protocols the magical IPv5, so instead of using those, they just jumped to IPv6, which is, like you said, IPv4 is not enough information. I think somewhere in here it says that light switches can't even use IPv4 anymore.
Right. So there's reasons why, and we're going to get into reasons like why. We'll see why IPv6 is necessary.
Cool.
And so let's start with that right now. So we're going to talk first about the format of the IP address that's used in IPv4. Well, it's a 32-bit number. And, again, remember bits, right? You can think of an IP address as being 4 octets, which is just 8 numbers, of ones and zeros, right? So this means that because the addresses are technically binary numbers, we can have 2 to the 32nd power addresses total on the internet. Now, the math for that's not important, but just believe me, that's true. Okay, that's a fact. Now, you can probably Google it to figure it out if you want. So, 2 to the 32 is, what is that? 4 billion,
294 million, 967,296. Sorry.
Right. Oh, okay. So yeah, and that probably sounds like a lot of addresses, but if you think about it, every single device on the internet needs to have its own unique address, right? Because otherwise routers just wouldn't know where to send the information. Because if 2 devices had the same IP address, how does it know which IP address to send, the information to? But there are more devices, or at least there will be, than that 2 to the 32 number, right? So that's the problem. We've run out of space in IPv4. Well, kind of, I guess. So there's another 32-bit number that I haven't talked about yet, and that is the so-called subnet mask. I don't know if you've ever seen subnet mask configuring like Xbox networking.
Yep, I've tried to do that, configuring a Wi-Fi for an Xbox 360. It was a pain.
Yep. So I'm going to teach you what that means.
Ooh.
Okay, so this is the subnet mask is to help us solve the problem, or somewhat solve the problem of the lack of IPv4 address spaces. So the subnet mask is what our router is going to use to know whether or not to send the information it has received out onto the WAN or to keep it on the LAN. You see, rather than have a unique IP address for every single device connected to the internet, we have this idea of public versus private IP addresses. Okay, so while both types of IP addresses look the same and have the same format, public IP addresses are used as like the actual IP address out on the internet. So in that 2 to the 32 number, only the public IP addresses are actually unique. Okay, so does that kind of make sense, the public-private? We're going to get a little bit more into that.
Yeah.
Okay, so, I mean, I'm guessing that's probably really confusing and all, so if I just give an example, I think this might make more sense. So if you think about your Wi-Fi network at home, you likely have a router which plugs into your modem, which is hooked into the wall through a coaxial cable, right? If you remember those coaxial cables from the episode on the physical layer, that's where you're going to be getting your internet signal from. So your ISP, or your internet service provider, which is like Cox, Time Warner, Charter, CenturyLink, any of those that you hate dealing with, well, they're providing you your internet connection through that cable hookup, or Ethernet hookup if you don't have a cable modem, or fiber optic if you have one of those. Lucky. What they're actually doing is providing you with a public IP address. Okay, so your public IP address is sort of like your doorway to the rest of the internet. Okay, so you might be wondering now, how can all of my devices use the internet if I only have one public IP address? Well, this is where that kind of ingenuity comes in. Your router's going to receive an internet connection from the WAN, right, the internet, and then your router will provide your house with a LAN, which is a private network all to yourself. So your router is going to issue private IP addresses to each of the devices you have connected to it, and each of these IP addresses is unique within that LAN. However, to the rest of the internet, each device that is connected to your router has the public IP address issued to you by your ISP.
Okay.
So when one of your devices wants to send information to another device, the subnet mask is checked in order for the router to know whether or not to send that information to a device within the LAN. So like if you have two phones connected to so if you and your mom are chatting on Facebook Messenger or something, and you're both connected to the same router, when you send messages back and forth, it's going to check that the subnet, that both IP addresses are on the same network. And so it's like, okay, I don't need to send that out to the WAN. I can just use the LAN connection and send it, to your mom like quickly. Okay. So that's what that subnet mask is for. Right. And yeah, so it just determines whether or not to keep it on the LAN or send it out to the WAN. Right. So that's why if you go to your command prompt on your computer, which you can just do by searching CMD if you have a Windows computer. On Mac, I honestly have no idea how to get there.
Isn't it like
terminal.
Notepad or something? I don't know.
No, it's terminal.
Oh, terminal.
That's the name of it. Just look for terminal on there, and that's your command prompt.
Okay.
But I don't know the command for Mac, because why would I use a Mac? Okay, so if you go to your command prompt and type in ipconfig, and you press enter, and you look on your Ethernet device or on your wireless adapter, you're going to see an IP address that's probably starting with 192.168 something.
Yep.
That is going to be different than if you went to Google and you just typed, what is my IP? That's going to give you your public IP address if you do the Google thing, because what your computer knows is your private IP address, and what Google sees is your public IP address, right? Because Google's accessing it through the WAN, right? Because it's out on the internet.
Yeah.
So that's why you'll see that discrepancy between the two numbers, because one's private and the other one's public.
And that's why they label it on Google your public IP address?
Right, that's correct.
Interesting.
Yeah. Okay, so hopefully you understand the public versus private IP address. I'm going to talk just briefly a little bit more about subnet masks. So most of the time, if you look at the subnet mask on your computer, it's probably going to look something like 255.255.0.0 or something like that. Something like all like 255s or 0, something like that. So you're probably thinking, okay, how does that tell the router whether or not to keep something on the local network or on the wide area network? In order to understand this, you have to remember that your computer understands this number to be in binary. And so this number is actually 11111111.1111.00000000 dot 00 eight more zeros.
So
right.
8 ones or 8 zeros, basically.
Right.
Okay.
Right. And so what this subnet means is that when your computer wants to send a packet of information to another device, it's going to look at this number to see which bits of the destination IP address, so the person you're trying to send something to, it's going to look at those bits on that IP address are so-called, it's going to see which bits are so-called network bits and which bits are host bits. So host bits are ones that mean that you're on the or that means that they're unique to that device within that network, and so the network bits will be the same, the host bits will be different. Okay, so this is sort of complicated, but I'm going to do my best to explain this difference here real quick. So again, just remember that your computer thinks of these IP addresses and subnet masks in binary, so if you're trying to think of them in decimal, it's not going to make much sense to you. So let's just say you want to send some information from your device to another device. And for simplicity's sake, your device has the IP address in binary 10101010. Now, it's not going to be that because obviously that's only one octet and your IP address is 4 octets, but just for the math's sake, it's going to be simpler. And then suppose the destination device has the IP address 10101011. So all the same except for the last bit. Okay, so now let's suppose that the subnet mask is 11110000. Now, what will happen is if the subnet mask's value is a 1, so from like left to right, then the bits corresponding to that same position in the two IP addresses have to match for it to be on the same network.
Okay.
If the subnet mask's value is 0, then it doesn't matter if the two IP address bits match. So in our first example, the first bit in the subnet mask is a 1. So that means that the source and the destination IP address's first bit has to match, which they do in our example, right? Now this is going to continue for the first 4 bits because those are the bits in which the 1s are in the subnet mask, right? Because there's 4 1s to start the subnet mask. So in our example, the IP addresses are a match, which is going to tell us that both devices are on the same network or LAN. Now, if at any point they did not match, then the router would know that it needs to be sent off to a different network or through the WAN, right?
Okay. So
yep.
So just to just some thinking here that I've done, as well as like following that command prompt thing. So you have to match the first 3 octets within the IP address to be on the same LAN, I believe.
If the subnet mask is 255.255.255.0.
Okay.
But if it was just the 255.255.0.0, then it would only need to match the first 2 octets.
Okay.
And what they've done now is, so this is called, I believe it's called class full IP addressing. This version that I just told you.
Yeah.
They've moved to what's called classless, which introduces a different kind of notation called CIDR notation, which is a whole other bag of worms that is really...
We don't need to open that up right now.
Right, but the concept's the same. It just makes it so it doesn't have to be all or nothing on an octet. Like you could have 111111111100.00.
Okay.
So like, you could have zeros within the same octet.
Okay.
Just so, because that will give you more, IP address spacing because you can do more with subnetting.
Yeah.
And so, yeah. So that's CIDR notation. So if you ever see that, it'll probably come across as like, you'll see an IP address and you'll see like a /12 24 or something. So that's called CIDR notation. So if you ever come across that, just know that it's referring to how the subnet mask works.
Okay.
And you don't need to be intimidated by that. Okay, so that's the basics of IPv4 addressing. I mean, there is a lot more, though, if you're interested. So just Google it if you want to learn more about that. So now that we kind of know IPv4, we're going to talk briefly about IPv6. Okay, so IPv6 was created in order to solve the address space problem of IPv4. Now it does this because IPv6 addresses are 128 bits as opposed to 32 bits. So with IPv6, there are 2 to the 128 possible addresses, or 3.4 times 10 to the 38 addresses. Now, this obviously solves our issue because that is a ridiculous amount of addresses that will likely never be used up, at least not in our lifetimes, right? So IPv6 doesn't have this idea of subnet masks. Every device has a public IP address, because there's enough addresses, right? Okay, so you're probably thinking, why did I just learn all about IPv4 if IPv6 solves all our problems? Well, it's because people hate change. Because we've always used IPv4, and IPv4 uses certain packet structures that our computers have come to expect. And, changing that with IPv6, which, also will change the packet structures, that is going to cause compatibility issues and problems. But we're slowly but surely making modifications throughout the internet that will allow IPv6 to be used as kind of an extension of IPv4. In fact, many ISPs and phone companies are mandating that different domains provide IPv6 support. So, who knows? We might get there someday. But basically, any really old technology that's still being used today is because people hate changing. So
it's true.
Yeah. So that's IP addresses, more or less.
Cool.
So now we're going to talk about the protocol data unit, which is the packet. Now, packets are the way in which information is structured at this layer at the network layer of the internet. So within a packet, there are a few different I'm sorry, that
keep the struggle.
Not cutting that out. So within a packet, there are a few different pieces of information that are of interest to us. Now, the first piece of information is the network addresses of both the source and the destination. Now, what I mean by this is that the IP address of the sender and the IP address of the recipient are both stored within the packet. It's sort of how when you send a letter using the post office, you need to put both your return address and the address of where you want the letter to be sent on the envelope. I mean, after all, the information needs to know where it's going, right? Okay, so the second piece of information is what's known as the error correction and detection information. So essentially, the packet computes what's called a hash of the information it has, and then this hash is stored within the packet. Okay, so a hash is just a mathematical calculation that uses all of the information within the packet in order to compute it. It's just a value, like a mathematical number, right? And what hashes are going to do for us is that if any part of the packet is changed, or at least a good hash will do this. So if any part of the packet is changed, then the hash changes significantly, and thus we may know that someone has changed the packet in some way. It doesn't tell us how, but it says, okay, this hash is different from what I was supposed to be expecting, so it's different, right? And the packet may also contain an identification tag that allows the packet to be reconstructed from fragmented data, and that's the error correction part. I'm not going to get into how it does that because, honestly, I don't even know. But it's not really an important thing to know. Just know that it does it.
Okay.
So that's the second piece. Now, another piece of information is what's known as the hop count, or the TTL, or time to live is the name of this value. Okay, so when a packet is routed on the internet, it's going to be sent to and from many different routers, since there's a physical limit as to how far a signal can be broadcast, right? Radio waves can only travel so far, wires can only be so long, right? So like in our post office example, when a letter probably takes a few stops when it travels a long way, like the mailman has to fill up for gas and sleep at some point, right? So when a packet is sent from one device to another, it's given a certain value, like 128, for example. And this value is going to be based on the device it is sent from. So different types of devices will give different time to live values. So like Windows operating systems have value of, I believe, 128, whereas like Linux operating systems is smaller than that. And just kind of depends. Now this value is going to determine the number of hops, so-called, which is just, a hop is just either a router, device, or computer that the packet stops on. So it's the number of hops that the packet can be sent through before it's dropped. And again, those routers, devices, and computers are just like stops that the mailman makes, right?
Okay.
So the reason for this value is that sometimes packets can never reach their target for, a variety of reasons. So in that case, we don't want packets just infinitely looping throughout the network, right? Because that would just take up unnecessary bandwidth. So what we did was say, okay, if I can't find where I'm going within 128 routers, then I'm just going to give up, and not be sent anywhere, right? So that's what the time to live value is.
Yeah.
Okay. And then obviously the most important field in a packet is what's known as the payload, which is just the actual information that we wanted to send. So this would be the letter itself in our post office example. Now there are a few other fields that packets might have, like different protocols will have different structures, like including the length of the packet and priority. So some networks will actually order the packets based on priority of like how important it might be. So,
all right.
Any questions on that?
Not really. Other than a good part of your analogy would be that the thing not reaching the target would just be like the government inefficiencies of the mail service.
True. Sometimes they don't give up. Sometimes they just get lost.
Yep.
Is a fact of life. All right. That's a topic for another day. Okay, so now that we kind of understand the PDUs and the addresses of this layer, we're going to talk about an incredibly important piece of network hardware, the router. Now, I've already mentioned it, but we're going to explain it in a bit more detail right now. So, what do routers do? Well, they do kind of what the name sounds. They route network traffic. So what this means is that they are going to receive packets and figure out the best way in which those packets should reach their destination. The word routing just means taking those IP packets that we just talked about and forwarding them to their destination. Well, how does it do that? Well, a router has two network interface cards. If you remember back to thebestwaytoexplainit.com/7, where I talked about network interface cards. So it's got two of them, which allow the router to connect two different networks to each other. So if you're on one network and you want to send information to another person who is on an unconnected network, there needs to be some way in which your information can be sent to that network. And this is what a router does. It connects two networks and routes the traffic between them, right?
Yeah.
So this is our way of connecting different networks. So the internet is just the internetworking of all of the devices. Well, the way different networks are connected is through routers. So that's the purpose routers serve.
Cool.
So you might be wondering, okay, I own a router and I only have one network though. Why do I need my router then? But in fact, you do need to have your network connected to another network because this other network is the rest of the internet, right? Your router at home connects your local area network or your LAN, which all of your devices are connected to, with the rest of the internet, your WAN. So without your router, your devices couldn't send information to the rest of the internet since it would have no way to connect to the other network, the internet, right? And to be honest, your router is likely not just a router. It's actually a combination of a wireless access point and a router, likely. As I mentioned in the Internet Part 2 episode, a wireless access point just allows you to connect wirelessly to a network. So it gives you a wireless network in your home. The router does the actual networking stuff in terms of like this specific layer of the internet. Okay, so you probably have a router wireless access point combo.
Okay.
If I'm guessing.
All right. Yeah.
So, but most of the time we just call them routers because we don't like saying both.
Well,
in fact,
it would be a little cumbersome if we said, "Oh yeah, go unplug the router/wireless access point."
Right. So yeah. So why do we need routers to connect networks? Right? Can't we just hook them up without them? Right? Well, no, because of how the IP addressing system works, right? So if you remember the distinction between private and public IP addresses, Well, we need routers to make sure that the proper information goes to the proper place. So because of the public-private IP addressing systems, it is possible, and in fact quite likely, that your private IP addresses for your devices are used elsewhere on the internet or, in someone else's private network, right? Well, this is a problem because your IP address is supposed to be unique. Remember, we fixed this problem by having just one public IP address that represents your private IP address. So this public IP address is going to receive all of the network traffic that is supposed to be going to all of your devices. Well, this is a problem because this public IP address is not your device's actual IP address, so they can't receive the information that is meant for them. So what we need is a way for public IP addresses to be translated into the correct private IP address so your device gets the information that is meant for it. Now, this is one of the functions that the router performs. It does network address translation, or NAT, which performs this task. And there's also port address translation, which really has the same goal as NAT, but it has a few other features that really aren't important to talk about here.
And its name is Pat.
Right. So there's your NAT that you talked about last time.
Okay.
So that's what it does. It's translation of public to private IP addresses.
Cool.
Yep. Now, there's also there's a non-layer 3 function that I'm going to perform here, that I'm going to mention here that routers perform, right? And they perform DHCP, which is Dynamic Host Control Protocol. This is actually a layer 5 protocol. So it runs on layer 5 of the internet, but it does a layer 3 thing. That'll probably make more sense once we get to layer 5.
Okay.
So DHCP is a service that hands out IP addresses to those devices connected to the internet, and it does this automatically. So if you ever looked at the networking options in Windows, there's an option called Obtain an IP address automatically. Now this tells the router to just give your device an IP address from an available pool of addresses, and it doesn't matter which one. Now you can also have your device get assigned a static IP address, which doesn't change. You will always have that IP address from this network. Does that kind of make sense?
Yeah.
So if you're on your Xbox and you want a static IP address, basically you're telling your router, whenever this device wants internet access from me, always give me this IP address.
Okay.
Whereas if you just had it configured to set up automatically, it's going to use DHCP to look and see what addresses are available, and you can configure what pool of addresses to pull from if you want to do some subnetting in your network.
Okay.
That's kind of complicated and stuff.
Yeah.
And so that's what DHCP does.
Hey, do you typically see DHCP/IP or?
Not usually.
I feel like I've heard that though.
I don't remember seeing DHCP very often, just because most networking, interfaces, they say just obtain an IP address automatically, or automatically assign my device an IP address.
Okay.
And that's what they're referring to, because it'd be a little bit technical to say use DHCP, and
Yeah.
nobody would know what that means.
Yeah.
So that's how they use it. All right. So that's DHCP. Now, okay, routers do all these things with their firmware. Okay. And firmware is just software that's encoded into the hardware that tells the hardware what to do. So if you think of this as being the hardware's operating system, right? You can usually access the router's firmware through opening up a web browser connected to your network and typing in the default gateway IP address. And you can usually find the default gateway by Googling the brand and model number of your router. And you can give it a look and play around with some of your settings if you want to learn more.
Cool.
You'll probably see a lot of the things we talked about, to be honest. And you're also going to likely need an admin name and password to log on. If you've never tried to get into your firmware, you likely haven't changed these things. Please change them now, though, because that's incredibly vulnerable if you just leave them as the default ones. Fortunately, though, a lot of routers are doing random ones that are assigned to each router. So if you just go to your router right now and you look at, it should have username and password on there, and that'll be how you get into your router.
Okay.
But for the longest time, they used to just ship them with the default ones. You could just Google it, and people that wanted to get on your network, they could just try and hook up to they would log onto your network through the firmware and, just use the default password and everything and just get control of your network.
Wow.
So definitely change it if you haven't.
They did not think that through.
Well, they did. It's just, I don't know. People have done some stupid stuff throughout technology's history.
Yeah.
So, yeah. But if you want to get into your firmware for the first time, either check the router. If it's an older router, you can just Google the default admin username and password using the brand name and model number of your router. So, like Cisco Linksys E2000 or something like that. Or default username and password, right? And there will be a list. And I don't know. Just look on Google. Basically, all technology can be learned by Googling. So
nice.
Yeah. Okay, so one more piece of hardware I'm going to mention, and this probably would have been more appropriate to mention it in the physical layer, but I forgot to talk about it. Sorry. And that's the modem. Now, it's likely that you have a modem at home, and you might not know why you need it. Well, modem literally stands for modulator demodulator. So basically what a modem does is it's going to convert the signals that come from your telephone line into signals that your computer understands. Nowadays, a lot of routers are actually router modem combos, so you don't need to buy two different physical devices. You usually plug these into the wall using a coaxial cable, and then you use an Ethernet cable to connect the modem to the router.
Okay.
Does that kind of make sense?
Yeah.
So the modem is just there because your computer can't understand telephone signals. Just, they're just they're encoded in a different way, but the modem's just going to fix that for you.
Yep.
So, yeah. So that's a modem, and yeah, we completed our tour of the network layer.
Man,
it's kind of complicated, but now you know way more about your network than most people, and probably way more than you'll ever want to know.
As complicated as it wasn't that hard to understand. So,
when you have a great teacher,
yeah, I'll commend you for that.
This is the best way to explain it.
Don't get too worked up, though.
Right. That's what they come to expect.
At least 50% of the time.
Right. Well, that's all I had for the network layer.
Yeah. I don't have anything to add, so there you go.
Yeah, so, you know what? Just a bonus. If any of my nerdy friends have been playing Xbox for, any extended amount of time, and they're just sick and tired of getting that strict NAT type, I'll just throw this in as a bonus. What you're going to need to do, Google port forwarding Xbox, I think will take you to it, and you just need to go to your router's firmware, what I just said, and you'll want to forward the ports in the same way that it tells you to on your router. So what that's going to do, it's going to open up those ports so that way the network address translation performs its function like for all people rather than just some. And so do that port forwarding or opening up the ports. That means the same thing, and that will fix your NAT type issues.
I should do that right now.
Yeah, so there you go. And I don't have the ports off the top of my head. In fact, we'll talk about ports in the next episode.
Sweet.
But yeah, just Google it, and it'll tell you exactly what to do. So
cool.
You're welcome, nerds.
Thanks, man.
All right. Anything else you want to add?
Nope. Got nothing. Other than
all right.
Throw us some suggestions at thebestwaytoexplainit.com /suggestions, and don't forget to drop a rating and review so that we can give you an Amazon Echo if you're lucky enough.
Well, right. Not everybody.
Yeah.
That's just gonna be a random drawing.
Yep.
So, yeah, like we said, better reviews are great, but be honest. Yeah. So that'll be ending December 17th. Drop us a review. Send it to Scott. Screenshot to scott@thebestwaytoexplainit.com, and that will get you entered into the drawing.
Nice.
Anything else?
I don't think so.
Sweet. Talk to you guys next time.
Get learning.